All right, it's my pleasure to introduce Friedrich Verlag, who will speak to us today about analytic theory of generalized Ricci flow. So please, Friedrich.
Thank you. Thank you very much for the invitation, and well, thank you all for coming. So from time to time I will just switch and check if anyone is still there. So because I don't. Okay. Anyway, if there are any problems with the connection, then do let me know. But hopefully it will be okay. Okay. So I would like to talk about the paper that we've put on recently on arXiv. So it's this one. You can see my cursor, I suppose, right?
Yes.
Okay, thank you. Okay, so it's about analytic theory of generalized Ricci flow. So in more detail, what I want to talk about is how to develop some basic aspects of the theory of the generalized Ricci flow in a way which as closely resembles the classical case as possible. I mean, well, yeah, and it is somewhat surprising that this somehow seems to be possible to some extent. That you can really develop the notions very much in parallel with the standard ones. Okay, so let me tell you exactly what I'm going to talk about. Okay, so let me start with a summary or. Okay. Oops. Summary. Okay, so the analogy that I want to draw is that, so we have the classical case. So in the classical case, we have a manifold, and the data is a manifold and a Riemannian metric, and we have an evolution equation for this, which is we have some one parametric class of metrics depending on some time. Let's see, on some t, some external parameter, and we want to evolve this according to the equation -2 Ricci. So this is an interesting PDE. Now in our case, what we have instead is that we have instead of a manifold, we have something that, I mean, assume, let me just check who is there. Okay, I assume you all know what the Courant algebroid is, but okay. So this is a Courant algebroid. I will still go through swiftly through the definitions to set the notation and all that. Okay, so instead of this, we have a Courant algebra. We have generalized metric. This is generalized metric. Okay, and on top of that, we also need to specify some extra datum. So, and this for the purpose of today's talk, this will be a half density. Okay, so I will explain all these things in a second. So far, let's just give you the idea. So half density on M. Roughly speaking, it's like a square root of a volume form. And okay, I should also say that the story that we present in the paper is much more general. So where we work with more general divergences, but for the simplicity of the exposition, I found it better to just focus on the half density case, because things are sort of easier to explain slightly. Anyway, the analog of this equation is then that the evolution of generalized metric is given by -2 times something that's called a generalized Ricci tensor, which depends on this data, G and sigma. And there is also a second equation for sigma, which is that it evolves as -1/2 of a scalar curvature, which again depends on G and sigma only. And then this is multiplied by sigma, so that it's a half density again. So, so physically, well, I think it's different colors. So physically, this guy is the one in string theory that covers G and the metric and a 3 form, and this guy here is the one that's responsible for the dilaton, say phi. And more generally, and actually I want to be more general, so this is like a very general setup. This thing will also include the gauge field. So this will well describe this kind of very general setup related to, let's say, heterotic string theory. So the equations the equations when you write them like this are kind of short and nice. So if you expand what this really is, then let me now use this trick that I prepared. So if you really write down explicitly what this is, then it's complicated, but it's like a known and well-studied system. So yeah, okay, this is just for show. Okay, so we will be working completely generally in terms of generalized geometry, again for generalized geometry, and all these things kind of will just be sort of simple but maybe painful consequences. So like all that we will do will be kind of elegant and simple, and just like then when you break it down to components, and you recover this kind of interesting and complicated systems. Okay, so the results that I want to get to are mostly the theorem for the short time existence and uniqueness of solutions of this equation. So we just say short time existence and uniqueness. And then there are some other results that one can derive along the way and or related to this. So for instance, one of them is that if you flow, then along the flow you can write down a very nice evolution equation for a scalar curvature. So along this generalized Ricci flow, this thing is okay. Forgot that. So there is some kind of Laplace operator that I will again define later on, and then there is some positive quantity. And one consequence of this is that supposing you're on a compact manifold and all that, so then the infimum of the scalar curvature is non-decreasing. So that's one statement. Then you have other statements. So for instance, you can show this lambda monotonicity result. So one thing I forgot to say before is that actually some things in this generalized case become somewhat almost more transparent than in the classical case. So like kind of studying the generalized geometry also seems to shed some new light on the classical case. And well, can I say it like that? Yeah, okay, maybe. So one thing I wanted to say here is that actually this flow equations that you have here, you can describe them neatly by saying that there exists a certain functional depending on this G and sigma. So this is the Einstein-Hilbert functional or generalization, where you simply integrate this scalar curvature against the square of sigma. And it turns out that this flow is the gradient flow of that with respect to some natural metric on the space of all possible generalized metrics and half densities. And so, okay, returning back here. So if you define lambda of G to be the infimum of S, G sigma, when you run over all possible sigmas with some unit mass, then this thing is non-decreasing along the flow as well. So so if along the flow you take T1, T2, T2 bigger, strictly bigger than T1, then you have the lambda of G at T1 is smaller or equal than this one, but in fact more is true. So and what you can show is that so the equality is attained if and only if this is in fact a soliton. So and well, let's say equality if and only if it's a soliton, where soliton is essentially just something that doesn't really evolve. It's just an example of a setup where you're just evolving by a diffeomorphism, or in this case, generalized diffeomorphism. Okay, and then you can use these to prove some other stuff. So you can look into the paper. This is just like to sort of highlight what is coming. Okay, so what I want to now do is kind of to build up the framework and then get at least here. So okay, are there any questions? Let me switch to you. Okay, I don't see any questions. Very good. If there are, then just interrupt me. Okay, so here I prepared some part about Courant algebroids because I sort of suppose that people here will be more or less familiar with it. So this I won't be writing it so that it's faster. So let me just briefly recall what the objects are and what is kind of the basic setup and what is the notation that I'm going to use. So Courant algebroids. So yeah, let me recall. So it's a vector bundle together with some extra structure, namely a bracket, a pairing on the fibers, and a vector bundle morphism, which is called the anchor map, which goes from E to Tm. And there is some bunch of axioms. So there is the Jacobi identity or the Leibniz identity, depending on which nomenclature you prefer. And then there is, again, a derivative property with respect to multiplication by functions. So this f here is a function. There is the invariance of the inner product with respect to the bracket or the action of sections. So, well, this is the invariance of the inner product. And then the most mysterious property is this one, that it says that the symmetric part of the bracket is not, in general non-zero, and it's governed by the inner product. And here I'm using this curly D, which is just a map that goes from functions to sections of the Courant algebroid. And yeah, and concretely, it's just given by the Durham differential, which takes a function and creates a one form or a section of T star M. And then we use this dual, which goes from the dual of this, so from T star to E star. But I will use throughout the talk the identification of E with E star, which is provided by the pairing. So this is what I'm using here as well. Okay, so this is kind of like a natural differential there. And okay, yeah, so this is the definition. Then you can show some things that follow from it. So for instance, the bracket, so the anchor map preserves the brackets. So it intertwines the bracket on the Courant algebroid with the commutator of vector fields. And the image of f is left central. So whenever something is exactly with respect to this d, then if you put it in the left slot, it just always gives 0 in the bracket. And then, very importantly, if you compose row, sorry, this was supposed to be the other way. If you compose row star with row, then you get 0. So these are just some simple by some simple manipulations. You can show this from the axioms. And now, so the last one essentially says that we have a chain complex which looks like this. And so we say that the Courant algebroid is exact if this is in fact an exact sequence. Okay, and more generally, we say that the Courant algebroid is transitive if we only have exactness at this slot, or equivalently exactness here. So, in other words, when rho is surjective, then we say that the Courant algebroid is transitive. And so the main structural theorems in this are these two theorems of Powell, Chevera. So the first one says that every exact Courant algebroid is of this very concrete form. So it's T plus T star, tangent and cotangent bundle, and the direct sum over manifold. Anchor map is just a projection. Pairing is a pairing of vectors and covectors. And the bracket is given by this explicit formula where L is the Lie derivative. And this H here in the last term is any closed tree form on M. Yeah, so I mean, more is true. It's like if you want to classify them, then you can actually show that if you have two such structures with their tree forms differing by an exact piece, then you can show that they're actually isomorphic. So the proper classification here goes by the cohomology, but we won't be using that today. So this is just to give you an example. So this is an exact Courant algebroid, so they are fully classified by this theorem. Transitive Courant algebroids are more complicated, but at least you can perform a local classification, and you can show that every transitive Courant algebroid is locally of the form which looks like the one above, but it has an extra piece. It has a so okay, I wrote it like this, but what I mean is really like a product bundle of M with a Lie algebra with an invariant pairing. Okay, and you can similarly write down the formulas, but it's slightly more nasty than the ones above, so I didn't write them. And importantly, this is just a local classification. So locally, this is always determined in terms of a Lie algebra. But there is some non-trivial isomorphisms, how you can glue things, and so if you want to make it global, it's more complicated. But again, I won't go into this. Okay, so some other stuff which is perhaps standard in some sense, but maybe not super standard. But this is often used by physicists in particular. and we will be using it as well. So so whenever you have a section, let's call it X, then you can use this section to act on various things. You can act on other sections by simply using the bracket. And we know that this is a derivation of the bracket. So this is the Jacobi identity. But also you can act on a function by transforming this X into a vector field by the anchor map. And well, you can just now use the usual approach from ordinary geometry, and you can extend it by as a derivation by Leibniz rule. You can extend it to act on any tensors. So then I will just call it curly L of X, so generalized derivative. Generalized derivative. I'm not writing E star here, so I mean, in principle, I could put like tensor product of E's and E star, but I will identify E and E star throughout the derivative. Okay. Now, okay, so this is just a bare Courant algebra structure. Now, what if you put more stuff on it? So first of all, let's talk about connections. So Courant algebra connection, or generalized connection, or just a connection, is this operator D, again in parallel with the usual geometry, which takes two inputs and creates another one. So it takes two sections, produces a third one, and in first slot it's function linear. So if you on the first slot, as usual, is written as a subscript. So if you multiply this by a function, you can take it out. But if you multiply by a function the thing you're taking derivative of, then you get an extra term. And this extra term, if you look at it, looks precisely, so this is the same formula that you have when you do X, the bracket of X and Fy. I mean, it's analogous to just, okay. And because of this, you can just as before, you can extend this to act on an arbitrary tensor in terms of the Courant algebra. Okay, so it's not just the lead derivative, but also the connection in the usual way. And so to finish the definition of a Courant algebra connection, we will also require that this, in this sense, that this derivative preserves this invariant pairing that we have on the Courant algebra. Okay, so this is the natural counterpart of a connection. And now we can also define some other stuff, such as a torsion. So torsion of a generalized connection, of Courant algebra connection, is given by this expression. So it eats two sections and produces a third one, but in fact you can show that, just as you maybe expect or hope, that this is in fact a tensor in all three slots, and it's furthermore a completely antisymmetric tensor. So I could have written E star, but again, E star is the same as E. Okay, so this is what it means to be a connection. And okay, just to finish this, this part, let me say that, okay, maybe you are very familiar with it, but let me still stress it. So it will be very convenient for us to use this kind of, I don't know how I should call it, but like, anyway, this kind of notation that we just, whenever we have a local frame, let's say E alpha of E, then whenever you write an expression that looks like this, that it has indices, it doesn't have sections like here, but it has on indices everywhere. Then this means that what we are really taking is that we are stripping all the indices away. We're just taking a repeated covariant derivative, and then we are evaluating the components of that. And this is this differs from, like, well, if you break it down, this is what it equals to in, like, this old-fashioned notation. The reason for this difference is that like when you have a tensor and you hit it with your covariant derivative, then you create a tensor that has one extra index, and then with this first derivative we also act on that one. So this is why it actually contains both of these things. The advantage of this notation, I mean, maybe you're all super familiar with it, but the advantage of this notation is that, like, whenever you work with such things, then every term itself separately is a tensor, so it's a component of a tensor. While this thing itself is not really tensorial in alpha, beta, gamma, delta, but like such a thing always is. and it will be very complicated. Sorry, very useful to you to employ this notation in what is going to follow, because otherwise it will be horrible.
What is the notation for the T?
What is the notation for a second?
Thing that's like that's to the right of the T?
Next, this one?
No, above. Like
This one?
to the left.
This one? Wait, so let's be okay. So you mean this whole thing?
Well, I understand the D alpha, D beta, T, and then I don't know what.
This is just as an example. I took a tensor which was in a tensor product of E with itself, so it has two indices. Like, so these are indices of T, like T index gamma delta component of T. Is that what you mean?
Oh. Oh, I see. You're using the frame.
Yes. Yes.
And then you take the gamma delta component.
Yes.
Okay, got it.
Okay. Yeah. Thanks. Right. Okay. So with this notation, before actually employing that notation, let me define a couple of more concepts. So first one is a divergence. So a divergence is an operator of the following form. It takes a section and produces a function on the base, and it satisfies this derivative property that if you multiply your section with a function, then it's the same as if you would take the function out, plus there is a derivative term where you use the anchor to map x to a vector field, which takes a derivative of f. So people usually, the common citation for this is Alexeyev and Shu, but as I learned recently in Madrid, the talk of, sorry, this was not in Madrid actually. Well, there was anyway, as I learned recently in Mario's talk, then apparently there is this older paper by Kosman, Schwarzbach, and Monterde where they already define it in some way, some more general setup. Okay, and well, anyway, the main example of such a construction is that whenever you have a section, you have a connection in the above sense, then you can form an associated divergence by taking the trace of that connection, and this will have that derivative property. Okay, so you take your section X, you take d of X. This thing will now have two indices, so you can trace. Well, I mean, you can trace it. Get a function. Okay, and finally, this is the final piece that we need technical. So let me just briefly recall the definition of densities, or like W densities. So W, okay, so suppose that you have a number W, a real number, maybe 1, 0, then W densities on a manifold is by definition just sections of a particular line bundle, and this is the line bundle that's constructed from the frame bundle by the associated bundle construction, where as a representation you take this one. So you take a matrix and you take its determinant and then its absolute value, this is crucial, and then you raise it to a power of W or minus W. So well, what this gives you is that it's a line bundle, and it's a very handy one because, for instance, when first of all, these line bundles that you get in these line bundles of W densities, they are always trivial, but the trivialization is non-canonical, and furthermore, you can. It's not just a line bundle, but it has kind of like a canonical positive and negative part. Like you can say what it means to be a positive and what it means to be a negative density, and that's because in this you have this absolute value. So if you think about it, then this is a consequence of that. And okay, so for instance, if your manifold is oriented, then you can think of one densities as simply top forms. So there is a canonical identification. But so you can see these densities as kind of like a more general thing that you can do even when you don't have a orientable manifold. But more importantly for us, we will be using Hauck densities, and so Hauck densities are particularly nice because they if your manifold is compact, let's say, then they form a Hilbert space. So sections of this line bundle of half densities is form a Hilbert space, because you can take two of them, you can multiply them, and well, that gives you a one density, and one density is something that you can integrate. So this is kind of the type of objects that we will be interested in. So we can take this H to stand either for half density or for a Hilbert space. And I will use this notation where I will call it H star. Maybe H plus would be more appropriate. So this thing will be positive half densities, like half densities that are positive at every point. So non-zero, but even stricter, they're always positive. And okay, and if you have such a thing, if you have a sigma which is everywhere positive, then you can again define the divergence associated to it, and this is again the divergence in the sort of the usual sense that you take your sigma, square it to create a density, and then you take the Lie derivative. You look at how that density transforms under the flow of your vector field, and your vector field here is rho of x. So you take the Lie derivative. This is not the curly. Sorry, this was supposed to be the ordinary Lie derivative. Right, and yeah, so you take a Lie derivative, you get another density, and then you divide it by your sigma, because your sigma was invertible, was non-zero. You can also just use the derivative property to write this as, to get rid of the 2's here. So okay, so the upshot is, as far as these divergences are concerned, that divergences there is essentially two means to construct them. One of them is you take a trace of a connection, and the other one is that you take a divergence with respect to some volume form or some density. Okay, so this is the end of this part where I try to set up the slightly more standard things. And now let me talk about the main bit, so the generalized Riemannian geometry. So before that, are there any questions? So no questions. Okay. Okay. So for whatever is going to follow, always think of a fixed courant algebroid in the background. So fix a courant algebroid E. And now we will be studying the analog of Riemannian geometry on it. So first, definition. So a generalized metric. So this is a very negotiable, very flexible definition. Depends on what you want to do with it. So there is kind of like a standard thing that this should be, but then you can put more conditions. So first of all, you say that this is an endomorphism, or there are equivalent ways to say this, but we will stick to this one. So this is an endomorphism. Like a vector bundle endomorphism, curly G that goes from E to E. So at each fiber, so this is like a fiber-wise thing, has no derivatives, and its main properties are that it squares to the identity, and that it's symmetric. So if you transpose it, you get itself. Here I'm using again that on your Courant algebra there is a canonical pairing. There is a not canonical. Sorry, there is like a part of the definition of Courant algebra is a pairing. So whenever I write things like this, what I mean is with respect to that pairing. Okay, so this is kind of the bare minimum that you want from your generalized metric. And if you have such a thing, then because it squares to the identity, then essentially you can decompose. It also okay. I guess you also need the symmetry of it. That out of this, it follows that that E splits as a vector bundle into a direct sum of V plus and V minus, where V plus and minus are the plus minus one eigenbundles of E. And so for today, I just to again simplify the presentation and to ensure that some positivity that we are going to need is satisfied. So I will put some further conditions on the generalized metric. So not just the standard ones, but I will also assume the following three things. So first of all is that G is positive definite, by which I really mean that if you, it's an endomorphism. So if you take this thing, it's positive definite. This is just to have some analog of the Riemannian story, and also to get some positivity that we want. Second one is that if you restrict your anchor map to V plus, so the anchor map, which in general went from E to Tm, if you restrict it to V plus, so it's a map, it's a bundle map from V plus to Tm. So we want this to be an isomorphism. This plays a similar role to the first condition. It kind of ensures that some nice properties are satisfied, and also in all the examples that I know of, essentially, like this is satisfied. So this is the one that you want if you want to describe like heterotic string or the NS sector and all that. That's kind of an example of this one, as far as I know. I mean, in those examples, definitely, I would have to think of like an interesting example which does not have this property. But I will also assume a third thing, and this is just this is slightly annoying, but again, it doesn't exclude an interesting case. So I will assume that the rank of these V plus and V minus are different from 1. And rank of, again, this doesn't exclude any interesting case because it only excludes like one-dimensional things. You don't really care about them. The reason for this kind of weird-looking condition is just that the following theorem that I'm going to write requires this, and hence the rest of the story that I'm going to discuss. So the ultimate results, such as like the existence and uniqueness, is expected to hold also when one of those equals 1, but it just requires a different type of analysis. And because those cases are not interesting, not terribly interesting, then I will just exclude them. Okay, so this is the end of the definition of generalized metrics. So essentially, it's an endomorphism that squares to the identity, and it's symmetric, and it satisfies some nice technical properties. Okay. Okay, now some notational remark. It will be convenient to kind of have a specific name for frames of V plus and V minus. So frames of, so whenever I need to take a frame, I will take an adapted frame to this splitting. So I will have some basis of some frame of V plus and V minus, and this I will usually denote with Latin letters. And this thing will be, well, Latin letters, but with heads, or dots, or bars, or whatever, but I will use heads. So these together is what I previously called E alpha, E beta, etc. So I will just split it. Okay, and another notation, a space of generalized metrics, I will call it M. This is like all generalized metrics on a given current algebrate. Okay, and yes, okay, and one observation about this space is that it's kind of easy to describe the tangent space to it. So if you have a specific generalized metric and you look at you are trying to deform it, and you are looking at these two conditions, then well, by taking derivative of the first condition, you will see that this is the same as, actually, you can describe it as some chi's that go from E to E and are symmetric for this condition, and anti-commute with G. So this is what comes by taking derivative of this property. This is 0. In more concrete terms, this means that these chi's, they carry two indices, so it's like chi alpha beta. And when you look at, oh, okay, write like this. So what these two conditions actually say is that if whenever you have like chi AB or chi A hat B hat, then those things vanish. And the only non-zero thing that you have is something that looks like A B hat, and this one equals to the one in the opposite card like this, B hat A. Okay, so this is how infinitesimal. Yeah, question?
Not with a minus?
You mean in here?
No, the one on the bottom.
Good question. So the thing is that so maybe I'm very condensed in this notation. So this thing, okay, let's see. So all these things are endomorphisms. So when I write something like this, and then I take like the alpha, so this is an endomorphism. So if I take like alpha and beta part, oh yeah, okay, I think this okay, yeah. So if I would, I mean, yes, you're right. There should be some sort of minus, but the point is that I'm. Wait, what am I saying? Okay, let me do the calculation. So this thing is chi alpha gamma, and then gamma beta, plus the other way around. Okay. Gamma chi gamma beta, and I'm in fact interested in. Okay, let's say like this. Oh, and I'm interested in the case when, first of all, I put index alpha down. Wait a sec. Yeah. Okay. Let's now suppose that this index alpha is in V plus and the other index beta is in this B hat. So, okay. Yeah, sorry, I should have prepared this. So, right. So the thing is that, well, here we are still summing over all gammas, but this generalized metric, it acts on V plus with eigenvalue +1, on V minus with eigenvalue -1. So this kind of means that this is only non-zero if this index also attains a value with a hat. This thing has to be some, I don't know, C hat. And then this thing is proportional to the identity with -1. So this is actually -1. Okay, so this is like minus delta C hat B hat. So sorry, this was just first term, but yeah, there will be a minus in there. So these guys together, it's just chi minus chi A B hat. And for the second bit, there will be a plus. So this is G A again gamma chi gamma B hat. But now I have G on the left. So this thing, in order for this is non-zero, this thing has to be a index without a hat. So this is like, oops. This is some C. And this is now proportional to the identity with coefficient plus. So this is the same as delta AC. So now this thing gives you a, yeah, this whole thing is 0. So this whole thing is just chi A B hat. And since it's 0, then it, wait, did I mess something up? What did I? Okay, this is indeed 0. Okay, but it was not very helpful. Okay, then maybe let me just say that it follows from the symmetry that this is yeah, I guess it's just from there. Sorry, yeah. So yeah, this was not. Okay, yeah. So forget what I was doing here. Let me erase this. Yeah. I think what this condition tells you is only this first bit, that these guys are 0. Yeah, that's what it says. Yes. Yeah. So if you break it down in the same way that I did it here, but you take the other combinations of coefficients, then it will show you that these guys are 0, and this second thing is just a consequence of the symmetry of this guy. Yeah, sorry, it's just like this. Is okay?
Mhm.
Yeah, sorry, I got confused. I thought it had to do with this G. But yeah, it's just the symmetry of that, because we are choosing generalized metric here to be by definition symmetric. Okay. Yeah, sorry for the digression. Okay, very good. So now definition. So let's fix E and G, and now we say that the connection D is Levi-Civita if the usual things. So D of G is 0, and the torsion of D vanishes. Where, again, this is the torsion that we define up there. Now, the important theorem here, this is by Mario. In his 2016 paper. So it says that, again, the theorem is a bit more general, but for our half density purposes, I will state it like this. So for any invertible half density or any positive half density, and for any generalized metric, there exists a Levi-Civita connection D with the property that the divergence induced by that connection, so the trace of that connection, is in fact the divergence given by this half density sigma. Okay, so not only you have for every generalized metric there exists a Levi-Civita connection, but there is many of them, and you can even choose the one which you like, which has a prescribed divergence. But unfortunately, this still doesn't fix them in general. So in general, there will be more of them. So again, I will use the notation. I will say that D is in LC Levi-Civita of G and sigma. Okay, so these are the connections that are Levi-Civita for G, and they have this compatibility condition with the divergence. So their trace is the divergence of sigma. Okay, and this is in general, well, by the theorem it's non-empty, but unfortunately this is an affine space modeled over sections of some bundle, so it's like infinite dimensional. Okay, now you might have noticed that I haven't really proven anything, so that I sneaked in this little proof that's kind of a cool statement by itself, and also it's something that people would expect, so it's better to have that. So let me state it as a proposition that for any D in LC of G and sigma, right, so we can define this operator that I will call Laplace, maybe Laplace G sigma, and using the notation above, this thing will be just this dA dB d beta, d alpha d beta, which is, well, I mean, if you break it down, this is really the same as dA minus dA hat, where again I'm using the fact that on V plus this thing is the identity, and on V minus this is the minus identity. And throughout, although I didn't say it explicitly, whenever you see raised and lowered indices, I always use this Courant algebra pairing to do that. That's what I meant about when I said that E will be identified with E star using the pairing. Okay, so there is this operator. In principle, it can act on any on any tensors, so sections of an arbitrary power of the Courant algebra. Okay, so this is the definition, and the claim is that well, if this is constructed using the Levi-Civita connection, I see. Yeah, sorry. Let me maybe not write this G and sigma, because in fact, as the definition as I wrote it, it uses the D, uses the choice of D. So it's not just a function of G and sigma, but also depends on D. Okay. Anyway, so the claim is that this is elliptic. Delta is elliptic. It's an elliptic operator. Okay. So now let me prove that. What do I have? Yeah, actually fine. Okay, so this is okay. So first, to prove that, I will prove this kind of slightly more unexpected thing. So instead of looking at this operator, let me take an operator where I contract these two guys using the standard pairing. So d alpha d alpha. Well, what is the symbol of this operator? Seen as an operator on on tensors. This maybe standard, slightly non-standard notation. So first thing to observe is that whenever you have a section of this, what it will look like in a frame is that you will have like a coefficient function, and then you will have like some member of the frame, tensor with some other member of the frame, some etc. And when you're hitting it with like these two covariant derivatives, that then whenever you hit a member of the frame, then you will get some Christoffel symbols. And so the only derivatives that you are going to get will be coming from whenever you are hitting the coefficient function. So consequently, what I'm really saying is that this symbol of this thing is the same as if you would look at this as a symbol by taking n equals 0, so only functions. So symbol of that is the same as symbol of this operator acting only on functions. Okay, this is what I maybe rather briefly try to sketch, but anyway, let's go from there. And so what is this? So suppose that I act on a function. So first thing to note is that this thing inside here, I'm taking covariant derivative of a function, and it's just the action of the anchor. So if you want to reformulate it somehow more nicely, then you can say that this is essentially this curly D operator from the beginning. So this is the composition of D transpose of the anchor, and then the alpha component of that. So this is just the alpha, curly df alpha. But now, if you look at it now, what you are doing is that you have a section of a current algebra, you take a covariant derivative, and then you are tracing. So this is just the divergence. So this is a trace of D acting on this curly df. But now you recall that, okay, we are actually interested in Ds which are compatible with sigma in this way. So you can write that this is the same as diff sigma curly D of f. And if you recall again what this is, then this is whatever. Point is that it uses the anchor map. And this thing is 0 because D was really a composition of ordinary D and star of the transpose of rho, which when composed with rho is 0. So this is 0. So so when this operator acts on function, in particular, it has its symbol is 0. Its symbol as a second order operator. That's something I should have said. Okay, so its symbol as a differential operator of degree 2 is 0. So this is 0. So what it means, so what if you go back, then what it means for this operator is that actually, although it looks like a second order operator, it's actually not a second order operator, but it's of lower order. So it's actually a first order or 0th order differential operator. Okay. Hopefully this was surprising, as it was for me. Okay, well, using that fact, then if we just look at our original Laplacian and just look here, dA minus dA hat, and now we just write again, like you use alpha as a frame for the whole thing, so this has both A and A hat, so you can write this thing as d alpha minus dA, and so overall you get 2 dA, and then this d alpha, which we just showed that has its symbol is 0. And the symbol of this thing is positive definite by these two properties here. Okay. You see that I'm getting slowly to the end, so I should. Okay, let me just say that. Yeah. Anyway, this is the symbol of this is positive, and this symbol of this is 0 on the second bit. So anyway, so the symbol is positive or invertible in this case. So it's elliptic. Okay. Yeah. Sorry, this was maybe more sketchy than I intended. Yeah, but it's a nice little thing to know. Okay. Okay, so I think I started slightly later, so let me maybe take another 10 minutes or so. Hopefully that's fine.
Yeah, that's fine. Yeah, you can take as much time as you need.
Thanks. Yeah, I won't take super long. Okay. Okay. So let me now define the curvature tensors. So okay, definition. So definition number 1. So suppose that D. So for D torsion free, it doesn't have to be Levi-Civita. For this, we only need torsion free. And there is also a version for when it's not torsion free, but we don't use that. So if it is torsion free, then we can define a Riemann tensor for it. And well, it will be something that eats 4 sections, so W, Z, X, and Y. And it's defined using our concise notation from before as okay, to look into my notes. W, Y, and then X alpha, D alpha, D beta, Z delta plus Z alpha. This looks absolutely horrible, but surprisingly enough, this was known already in some incarnation to Siegel in the beginning of the 90s. Okay. Like this, okay. So whenever I say commutator, you should just substitute in your head for this that I am taking this guy, and I am using that conversion from above for the coefficients of these covariant derivatives. So it's just like some absolutely horrible looking operator. Now the slightly surprising proposition maybe is that this is a tensor. So in fact, first of all, Riemann D is really a tensor, so it's a tensor. And furthermore, it satisfies the usual symmetry properties. So it's anti-symmetric in the first 2 bits. So let me just write it like this: usual physics notation. So this is the weighted anti-commutator, 1/2 alpha beta minus beta alpha. So it's anti-symmetric in the first 2. It's anti-symmetric in the last 2 bits. And it's symmetric with respect to the exchange of the first 2 and last 2. And it even satisfies the algebraic Bianchi identity, although we don't show that in the paper. This was shown in some other paper by Jurcho and Vysoky at least. And so, okay. We don't show this in the paper, but it's probably good to put it in here.
What does it mean when you put the brackets around the alpha beta?
So it means that the expression that you take, so this thing, for instance, it means that it's 1/2 Riemann alpha beta gamma delta minus beta gamma alpha, beta alpha gamma delta. So you take the whenever you have an expression and you put the anti-commutator in there, or sorry, like square brackets, it means that you take the sum over the permutation group of all possible permutations in here and weight it with a sign, the signature of the corresponding permutation. So in this case, it's like an anti-commutator. Sorry, I should maybe the proper word is to say it's like you take the anti-symmetrization of that. Yeah. You take the anti-symmetrization of that, but it's like it's weighted. So if it was already anti-symmetric, then this just leaves it in as it was. So it's like a projector. Yeah, or more concretely, just this. And the same here. Here you will have like 3 terms or 6 terms with signs. Okay. Oops. Okay, so this is the Riemann tensor.
That it's symmetric?
Say again?
What does that mean? Does it just mean that it's symmetric?
You mean this like for instance, this equality means that it's anti-symmetric in the like this first equality here literally means that that it's anti-symmetric in the first two indices. So it's like if you would exchange them, then it's -1. Yeah. So the trick is that like you have when you have an expression and you have like alpha beta in there, then you can write it as like a symmetrization plus anti-symmetrization. And what this equality says is that it's equal to its anti-symmetrization. So the symmetrization disappears. So it's like,
right.
So it's anti-symmetric. Yeah, this is the way physicists usually write it. It's kind of concise. Okay. Yeah. So now definition again. So suppose now that we fix a Levi-Civita connection. Now I want to define Ricci. So before defining Ricci, I define something slightly stranger. I define a Ricci bar, which we I think call full Ricci. So this thing will be just the thing you would normally expect. So a contraction of the Riemann tensor on 2 indices. And if you look at the structure, so we already showed that Riemann was a tensor, so this is tensor as well. So this Ricci bar is a map from E to E. And now I define what we really want is this unbarred proper Ricci, and I define it by taking this slightly surprising looking expression. So I take Ricci bar, everything here, Ricci bar and G are endomorphisms, so they are maps from E to E. So I take their commutator and then multiply it by G. In the end, what this means that this Ricci will again be some sort of map like this. And let me now tell you a proposition which explains maybe partly why this is the way we go. So proposition. First of all, both of these two guys are symmetric. It just follows from the symmetries above. So they are symmetric endomorphisms. Second thing is that actually what this definition does is that it projects out kind of nasty bits of this Ricci bar. So what it means concretely is that if you look at like A, B, so the plus plus or the minus minus bits, those are 0. And the only non-zero bit by symmetry is this A, B hat, and this one equals twice Ricci bar, the corresponding component of Ricci bar. So up to this factor of 2, what it does is that it takes this Ricci bar and you kind of truncate it so that it only contains this A and B hat, and conversely B hat A components.
You project it into the tangent space of the metric.
I'm not sure. Can you say it like that? I would just say that like you have all this thing lives in E tensor E, and you can decompose this into like V plus tensor V plus all the possible 4 possibilities. And this thing just says that it just like kind of kills this guy and the corresponding V minus and relates these two by symmetry.
Which way that you said before was the tangent space to the metric.
Right. Yes. Then in that sense, yes. Yes. And indeed, this is kind of what you want, because we want to write G dot equals -2 Ricci. So we want that like infinitesimal derivation, infinitesimal change of your metric is supposed to be governed by this. So this is kind of the reason why we are doing this. Yes. So yes, you're right. Yeah. Very good. Yeah, another kind of crucial property that explains why we are making this truncation of Ricci bar is that if you do this truncation, namely you define Ricci, then this Ricci in fact only depends on G and sigma. So although the definition was using a choice of a Levi-Civita connection, the resulting expression that you write only depends on this G and sigma. So we can write it Ricci G and sigma. So Ricci bar does not have this property, unfortunately. It depends on which Levi-Civita you choose, and so does the Riemann tensor. So the only true objects the only kind of object out of these guys that only depends on G and sigma is this Ricci so far. But there will be a second guy in a second. Just one final property. It's again kind of crucial for this. So Ricci only depends on G and sigma, but even its dependence on sigma is kind of very mild. So what this means is that if you take your sigma and you multiply it by you want to get some other half density, so you multiply it by E of F, where F is some function, then and you compare it with the original one, then this thing will only differ by an automorphism. So this thing will be minus the Lie derivative of the generalized metric with respect to something, and this thing concretely is G acting on curly D of F. So okay, whatever it is, but the point is that it's just a Lie derivative of the metric. So you are changing the Ricci, but only up to some sort of automorphism. Okay. Yes. Okay. Now, the final definition, hopefully, is the one for the scalar curvature. So now we have Riemann, we have Ricci bar, and we have Ricci. So we can define again. Take the Levi-Civita connection for G and sigma, and define R as the kind of like contraction of Ricci bar. With your generalized metric. So note that you cannot really contract Ricci because Ricci, the bits that Ricci only has this component and contracted with this generalized metric. Contracting this guy with G gives 0. So to really like mimic what happens in the usual Riemannian setup, you just want to kind of contract Riemann tensor twice, and this is what we are doing here. So if you take this kind of standard definition of the scalar curvature, then the proposition is that this guy again only depends on G and sigma, and that's point number one. The second point is that you can show some nice Bianchi type identity. So okay. So it's like a contracted Bianchi identity. So the question whether there exists a proper Bianchi identity for the Riemann tensor is sort of still open, and there are some works in double field theory literature where they seem to be claiming that it doesn't exist. But at least this one you can derive, and it's kind of useful as well. Okay. Now, for the sake of time, before announcing the final result, let me make one final proposition, kind of technical proposition. So suppose that you have a family of generalized metrics, so depending on some parameter S, and a family of divergences, family of invertible half density, family of half densities. And also suppose that you have a family of Levi-Civita connections corresponding to those at any given parameter S. So you have same as above, but you have like a family of everything. And now you're asking like what happens if you take derivatives of these quantities along this family. So for instance, what happens if you take Ricci and then you take a derivative with respect to S? So I will write a dot simply. And so now if I set chi to be the derivative of G, and if I set tau to be the derivative of sigma divided by sigma, so that I get a yes, sorry.
Sorry, I missed it. Is S a parameter?
Yes, S is a parameter. Yes, yeah. This is like a family. So, yeah. So the claim is that you can write this thing neatly in terms of these objects. Namely, we'll get this Laplace operator that we've seen above, and there is some other bit. This one. So this is a parameter of the Lie derivative, and then there is 2g curly d of tau, and this thing acting on g. So again, there is some sort of automorphism, like some action of the Lie derivative of something on the generalized metric, and then there is lower order terms. So by this I mean lower order in derivatives of chi and tau. So these are the second order bit. There is also further stuff, but fortunately for this analytic theory, many aspects that can be thrown away. And a similar thing holds for a scalar curvature. This one. And -4 and plus lower. Okay, so unfortunately I should finish soon, but so let me. I mean, I should have finished probably some minutes ago. Okay, let me maybe just highlight the fact that were it not so if there would be, if this term were not there, then knowing that this operator is elliptic would be great and super helpful, because then we could prove immediately that the generalized Ricci flow exists and is unique for some short time. So that would be great. Unfortunately, there is an extra bit, which is sort of similar to what happens in the classical case, but it's more subtle, slightly more subtle in this case. So to see how we treat that, you are invited to look at our paper. For now, let me just conclude, and let me tell you like the final bit. So generalized Ricci flow. Okay. So observation number 1. So when we take our space of all possible fields, so space of all generalized metrics times space of these positive half densities. So this thing has a metric, as a canonical metric. I mean, it's an infinite dimensional space, but like formally you can write it. There is a metric. So for instance, if you take if you take a tangent vector to M, so let me represent the tangent vector as G dot. So suppose that you have some family like above, and you have some family of metric, and you look at the tangent of that, and you take a pairing of that with itself, and you are sitting at a point of this space given by a G and a sigma, then it's kind of, well, there's only one thing you can write up to a prefactor, and that's you take the the norm squared of this, calculated with respect to the generalized metric, times sigma squared. It needs to be a density. So this is how it works on G's. And if you have two variations, two infinitesimal deformations of sigma, then similarly there is some coefficient, and you get this. And you want that these two things are orthogonal to each other. So it's kind of like not really a product, but these two directions are orthogonal. So there is a natural pairing on this infinite dimensional space. So for physicists in the audience, I should say that this is the relative choice of these signs corresponds to the choice of the renormalization group scheme in calculating the renormalization group flow for the nonlinear sigma model. And this particular choice here, the relative choice here, corresponds to the dimensional regularization, and it has some advantage for our story. And again, I invite you to read the paper. And okay, just having said all of this and defining the following Einstein-Hilbert functional. which is a map on this m times h star. And I think I wrote it in the beginning, so let me just repeat it. This is just the integral of scalar curvature times sigma squared. So then the definition is that the generalized Ricci flow is the gradient flow, or like I guess precisely half gradient is the flow of 1/2 gradient of S. So formally, you just take this metric, you calculate the gradient of this, and it will give you some flow. And if you just break down what that means concretely, then it's the thing I wrote at the beginning. This one and this one with a minus. And okay, and well, now performing all the hard proofs, you can show that in particular you have the short time existence and uniqueness of this flow. Existence and uniqueness.
Does that use the fact that it's a gradient flow?
Not directly. Yeah, not really, not directly. I mean, it is the story is kind of like very. It's in a sense very nice. So kind of all things. I mean, all things are kind of playing very nicely with the other things, and this causes some nice things to happen. But I think, as per se, but strictly speaking, in the proof itself, we don't use this, but we might use some proper. Yeah, I think we don't. We don't use it. I mean, Jeff might correct me, but I think we don't need, strictly speaking, that property
Well, I
for the
would
proof.
just say that like this sort of version of the gradient flow property, I don't think we use mathematically. I mean, this is kind of like a formal thing
Yeah.
that's motivated by, as Friedrich said, like the physics, but there's another gradient flow property yet to come, which most certainly does get used.
You mean? Oh, I see.
Or I mean, I guess you mentioned it at the very start, but I don't think you proved it yet, right?
No. But in fact, I for sort of for the lack of time, and I should really finish here. So
Yeah,
sorry for
sure.
that. I wanted
In
to
general,
stop
like
here.
for these evolution problems, like knowing it's a gradient flow. For instance, there are situations where you can say prove the flow is global in some sense and maybe controlled and not singular or whatever, and you want to know, well, does it even converge, right? I mean, the whole point is to try to construct solutions to supergravity equations, and so should it converge? And so what the gradient flow property tells you is that if it is controlled and non-singular in the appropriate sense, then it will converge. Does that make sense?
A little bit.
Yeah. Anyhow, yeah. Sorry for not really proving this big theorem at the end. But well, let me just say that the proof goes along the standard lines with some extra tweaks, and so it's not really along the standard lines, but like mostly there is some complications coming. Yeah, I just thought that people might be interested in hearing, or in particular about these curvature tensors, because I remember in Madrid people were kind of excited that these things worked, so wanted to highlight those bits.
Okay,
Yeah, I mean,
so that's it. You're saying you're going to stop there. Okay.
yes, I would maybe stop here. Thank you. Sorry for the rush towards the end.
No problem, no problem. Are there more questions?
Yeah, thank you, Friedrich. Yeah, may I ask? I mean, you mentioned that these half densities have like this very nice property that they are like part of a Hilbert space.
Yes.
And I guess the key reason why you need them and you need that property is precisely this thing that it's in, like, to define this metric somehow. Like you try to play
I guess.
Yeah, if you try to play the same game with something that is not a half density, then you just can't play the game, or like.
Yes. So there is actually several points where the fact where half densities kind of pop out. So there is this kind of very mysterious thing that still, to my knowledge, it's not really understood. And that with Pavel we found that there is some sort of Laplace operator. So let me maybe distinguish from this one. So it's like some Laplace operator, which is only associated to the generalized metric, and this acts on the half densities. Now, yeah, they need to be half densities, otherwise it doesn't work. If it acts on all sorts of densities, if you specify some sigma, but you can just construct a canonical operator using only generalized metric that acts on half densities. So for some reason, yeah. Well, that's observation number one. Another observation is that from this general theory of Courant algebroids, there exists this thing called the generating Dirac operator, and that thing also you can show that. Well, I mean, you have some choice in defining it, but actually, if you act on half densities, then there is a unique one.
Mhm.
And all of this kind of, I guess, is related to the fact that these things form a Hilbert space, very, very, very roughly speaking. But yeah, I guess you can say it like that.
I see.
So those things pop out. Just if you look at things properly, how they behave under like this dilatonics, whatever, like these R factors and all those things, then it's just surprisingly it seems to pop out at many places.
Mhm. Okay, thank you. Yeah, that's very interesting, very random in some sense that it's.
Yeah, I guess.
Yeah. Okay, thank you.
Thank you.
Any more? Okay, so yeah, if not, yeah, let's thank Friedrich again.